Hi everyone, very good afternoon to all of you. I mean good evening. So I welcome to all of you for this physics class which is on work, energy and power. So we are continuing whatever we had discussed in the previous class, and that was work energy theorem. Alright, so we are continuing work energy theorem, and to just, if we revisit whatever we have discussed in the previous class, that was that work done by all the forces is equals to change in kinetic energy. Okay, work done by all the forces is equals to change in kinetic energy. And when I say all the forces, I mean all the forces acting on the body, be it normal force, tension, friction, whatever. You have to consider all the forces and find the work done by all of them. That will be equals to the kinetic energy, the difference of the kinetic energy of the body. Is that clear? Guys, are you connected? Is audio video fine? Shillong Center, Itanagar, students from Manipur. Okay, so shall we begin today's class? So guys, first I'll take few questions on this theorem, work done by all the forces equals to change in kinetic energy. Alright, so let's start doing this one. Question is, suppose this angle is, let's say 53 degrees, okay, and the hypotenuse is equals to, let's say 10 meters. Okay, basically this is 10 meters. It is fixed, alright, at the bottom it is fixed. From the top, if I release a block, okay, if I release a block of mass m, and mass is given by, let's say 20 kilograms. Alright, the question is, if coefficient of friction is 0.3, find the velocity of the block at the bottom. Find the velocity of the block at the bottom of the inclined plane. At the bottom of the inclined plane. Shillong Center, your camera port is 8084, but no one is there. Okay, there is one student. Only one student is there. If friction is there, alright, if friction is there, then what will be the velocity of the block at the bottom of the inclined plane? Given that we have released it, okay, we have released the block from the top of the inclined plane. Anyone? Should I explain this? Guys, see, apply work energy theorem here, alright, and to apply work energy theorem, you have to calculate net work done on the block, okay, net work done by all the forces. How many forces are acting on the block? So if you make the free body diagram, see, we have mg acting in the downward direction, we have normal acting in this direction, and friction is acting in the back direction, all right, against the motion. If you take the components of mg, the components of mg will be, this one will be mg sine theta, this is mg sine 53, and this is mg cos 53. Okay, where friction is equals to mu into n, because maximum friction will act, the body is moving. Mu is how much? 0.3. N is equals to mg cos 53. Okay, I can write, where is control Z? Mu mg cos 53, because n is equals to cos 53. So friction is equals to 0.3, mass is 20, g is 10, cos 53 is, it is 3 by 5. Okay, so it is equals to, this will be 200, I mean, let's solve it. This is 26 into 6, 36. So friction is equals to 36 Newton. Is that clear? Okay, 36 Newton. That is the value of friction. So now we have to calculate work done by all the forces. All right. So work done by all the forces will have work done by gravity, work done by friction, and work done by normal. Okay, work done by normal. And since the normal force is always perpendicular to the motion, there will be no work done by normal. Okay, the body is moving in a perpendicular direction. So the angle between force and displacement is 90 degree always. And because of that, work done by normal force is 0. What will be the work done by gravity? Work done by gravity is mg sine 53 into L is how much? Hypotenuse is 10, so 10, plus work done by friction will be negative, okay, minus F into 10. Why negative? Because the body is moving down the plane and friction is acting in the opposite direction. So work done by all the forces is equals to, M is how much? M is 20. So 20 into 10 into sine 53 is 0.8. This will be 0.8. 0.8 into 10 minus friction is 36 into 10. So solve it. This is equals to 200 into 0.8. It is equals to 160. 160 into 10, 1600. 1600 minus 360, how much? This is equals to 1240. Okay, 1240 joules. Good evening, Jia. So work done by all the forces is equals to 1240 joules. And we know from the first law of, not the first law of, this was the work energy theorem. We know from the work energy theorem, work done by all the forces is equals to change in kinetic energy. Okay. So work done by all the forces is 1240 kinetic energy. It is half mv square minus half mu square. Okay, final minus initial. This quantity is 0. Half mu square is 0. So 1240 is equals to half. Mass is 10. I hope it is 10 or 20. Mass is 20. Na? I always get confused in the values. So half 20 v square. Alright. So it is equals to 10. So v square is equals to 124 and velocity is equals to square root of 124 meter per second. Okay, this was a very simple question. Is it clear to all of you how to do this? Is this question clear to all of you? All right, next question. Next question is easy, but it might seem difficult to you. The question is, suppose we have a wall. Suppose we have a wall. Okay. All right. We have a wall. The thickness of this wall is 1 meter. Okay, the thickness of a wall is 1 meter, and there is a bullet. There is a bullet which was moving with a speed of 800 meter per second. A bullet was moving with a speed of 800 meter per second, and when it leaves the brick wall, all right, it gets embedded and it leaves with the speed of, the bullet has a speed of, Control C, Control V, all right. So before striking the wall, the velocity was 800, and after coming out, it is 100 meter per second. Okay, this is the question. So a bullet was moving with 800 meter per second, strikes the wall, and comes out with a speed of 100 meter per second, because obviously the force applied by the wall. We have to calculate that force only. Okay, so the question is, the bullet mass was 10 grams. Okay, the mass of the bullet is 10 grams. Question is, find the average resistance. Find the average resistance offered by the wall on the bullet. Have you understood the question? Average resistance means you have to calculate the average force applied by the wall on the bullet. The mass of the bullet is 10 grams. Jia, can you do this question? Find the average resistance offered by the wall on the bullet. See, can I say work done by wall is equals to change in kinetic energy? Do you agree? Work done by all the forces is equals to change in kinetic energy. What is the work done by force? See, the displacement is in this direction. Force applied by the wall will be in the opposite direction. So it will be a negative force applied by the wall into the displacement, which is 1. It is equals to change in kinetic energy. So half m is how much? 10 by 1000, 10 grams, no? And it will be equals to v square minus u square. half m v square minus u square. I can write it like this. So let's solve it. Minus f is equals to half 10 by 1000 into v square will be 100 square minus 800 square. Okay, that's it. Solve it. The force will be equals to, negative sign will get cancelled out. The force will be equals to 3150 Newton. This is the average force applied by the wall. Understood this question? Yes, very good, Jia. 3150, very good. Force applied by the wall will be 3150 Newton. Okay, guys. All right. Now we'll start, or maybe I can give you another question if you want to, or we can start the conservative and non-conservative forces. Okay, I think we should proceed. So, the next topic is conservative and non-conservative forces. Now, what are conservative and non-conservative forces? So, there are certain forces whose work done does not depend on path. Alright? There are certain forces whose work done does not depend on path, it just depends on the initial and the final position of the body. These forces are known as the conservative forces. Alright? These forces are known as conservative forces. So, conservative forces are those forces whose work done does not depend on the path taken. On the other hand, non-conservative forces are those forces, for example, friction, work done of which depends on the path taken. Okay. So, the basic difference is between a conservative and non-conservative force, that conservative force are those forces or I should write to whose forces whose work done does not depend on path taken. It just depends on initial and final position. Okay, examples are gravitational force, electrostatic force, and spring force. Okay, forces whose work done does not depend on path taken is known as conservative forces. Got it? Okay. On the other hand, not all the other forces. Okay, non-conservative means non-conservative forces. So work done by these forces does depend on path. Work done by these forces. Okay, my handwriting is going really weird today. Work done by these forces does depend on the path taken. Okay, for example, friction. For example, friction. Okay, does it make sense? Now let me explain you how does it matter. Suppose I have this kind of path, okay, and I have this kind of path. I have two bodies, okay, they have same height h and h. Okay, they have same height h and h. At this, we have block M and M. All right. Now, work done by gravity in both the cases will be mgh and mgh if the block comes to the bottommost point. Okay, because in the direction of force of gravity, only h is the displacement. But work done by friction is greater here compared to work done by friction there, because we have larger path. Okay, I mean, I should say magnitude. So work done by friction is different because it depends on path. We have to measure the whole path. But for gravity, we just want to know what is the initial and final position and just calculate the displacement. That's it. All right. So that is the basic difference between conservative and non-conservative force. All right. Is that clear? Now there is one very simple way of understanding conservative and non-conservative forces, and that is why perhaps these things are named as conservative and non-conservative. So basically, see, imagine you take a block, all right, we will use the example of spring. Just wait a minute. Yeah. So imagine we have a spring attached to a block. Okay? You do some work. You do some work by applying force. And remember, this is frictionless. Surface is frictionless. Now, if you apply some force and do some work, that work will be converted into a form of energy which is still available to the system. Suppose if you remove your force, then your work is stored in a form of energy. All right. So when you remove your force, the block will have motion. So your energy is still present in the system. It is conserved. On the other hand, if imagine there is just surface without any spring and there is friction. Now push the same box by the same force. Now what will happen in this case? In this case, your work done is not available in the system. It is lost. All right. It is lost through vibration, heat. There are so many things in friction. So that energy is lost to the system. It is not available. Here it is available. And that is why we call this as conservative force, the spring force, and friction as non-conservative force. Is that clear? Understood? Yes or no? Shillong, Jia. पक्का? एकदम पक्का? How many of you understand Hindi? कितने लोगों को हिंदी आती है? हाँ? शिलोंग, जिया? I don't think many. Otherwise, I was thinking, there was a slight chance that I was thinking about, and that was, what if I start teaching in Hindi right now? हाँ जिया, तुमको तो आती है. You are in Madhya Pradesh, so you must know Hindi. But I'm not sure about Shillong or the other centers. Okay, so whatever. Now let's talk about potential energy. Now what is potential energy? It is a form of energy by the virtue of position or configuration of particle is known as potential energy. Okay, is known as potential energy. For example, I'm just giving you an example. See, if you take a mass which is on the ground, and if you take identical mass and if you take it to some height, okay, we have two bodies, A and B. So body B is ordinary, it is just placed at the ground. On the other hand, body A is at some height. So its position is different, and because of this different in position, this has an energy, and that energy is known as potential energy. That I will explain. Okay, that I will explain. On the other hand, if you imagine a spring, one spring is normal and one spring is compressed like this. Okay, so because of a different configuration, it has different potential energy and it has different potential energy. All right, so that is something what do we mean by position or configuration. Now let's try to explain what is potential energy. Okay, so please focus here and look at my pen. All right. So if I take my pen from this position and if I lift it to some height, all right, I have done some work. Okay. Now we all know the conservation of energy principle, that energy can neither be created nor be destroyed, and work is something, you know, through which energy gets transferred or transformed. So when I do some work, where has my work gone? There is no friction, there is no heat or vibration. So where my work has gone? Now there is a hint. Okay, to answer this question there is a hint, and that hint is release it. Okay, so when you release it, you will see when it comes to the bottom, all right, or you can say towards my hand, it has velocity. It has velocity means it has kinetic energy. Again, the conservation of energy principle. Where is this energy coming from? Okay, if we are talking strictly in terms of energy and not in the terms of work or force, you just talk in terms of energy. Every process can be explained through energy. All right, one energy transforms into another energy. So what process is going on here? All right, how are we getting this kinetic energy? From what process? What is the source of it? And guys, that is the potential energy present at this point. That potential energy has been converted into kinetic energy, and when we do work, our work is getting stored into potential energy. Okay, so that is potential energy. Or you can say, if you compress a spring by applying force, your work done is stored in this deformation of spring. Okay, and we are calling it potential energy. That potential energy can be reused to get motion. Okay, understood? That is potential energy. All right, so just remember this statement. It is applicable everywhere, all right, when it comes to potential energy. First point is potential energy is defined only for conservative forces. Okay, it is defined only for conservative forces. For example, gravity, for example, spring, for example, two charges or the configuration of certain charges. All right, only for these things we can define potential energy. We cannot define potential energy for friction. Is that clear? All right, the next point is potential energy. What is potential energy? Okay, try to understand this. So, work done by external agent work done by external agent against a conservative force gets stored in potential energy of the body. Work done by external agent against a conservative force gets stored in potential energy of the body. Just try to remember and understand this statement. Whenever you do work against a conservative force, your work done gets stored in the form of potential energy. One very simple example is this. See. By the way, I should say difference in potential energy. Potential energy is a relative term. Okay, gets stored in the difference in potential energy of the body. Okay, so if you take a block of mass m, all right, you apply some force which must be equal to the weight of the body. All right, so you apply a force equals to mg. Okay, or maybe I should write F, and we know F is equals to mg. You take this body from this position to this position. All right. Then what is the work done? Suppose this height is h. The work done is given by F into h, where F is mg, so mgh. Okay. So you have the external force has done work equals to mgh, work is equals to mgh. All right, and it is against conservative force. So this much is the difference in potential energy from these 2 points. Okay, suppose this is A and this is B. Then I will write UB minus UA, where U is the symbol of potential energy, it is equals to mgh. Is it clear or not? The same thing will be very useful for class 12th. Okay, when we'll discuss electrostatics. Work done by the external agent against the conservative force gets stored in the difference of potential energy of the body. Okay, potential energy has a symbol U. Okay, clear? Pakka? Shillong Center. All right. So let's put some points for potential energy. Okay, potential energy. So first of all, its symbol is U. Always remember this. Potential energy symbol is U. Symbol is U. Okay. Sometimes I will write potential energy as PE like this. Okay. Symbol is U. If you talk about unit, the unit, since it is energy, so its unit will be joules, capital J. All right. Then few points which are very important. Potential energy is a relative term. It is a relative term. Okay. So basically, we can only define, it means we can define only the difference of potential energy. Okay, only the difference of potential energy and not potential energy at a point. At a point. Understood the meaning of this? Potential energy can, we can only define the difference in potential energy, not the potential energy at a point. And the reason is very simple, because we are defining the potential energy in terms of work done. Alright? So it matters from which position to which position you have taken it, isn't it? If you want to calculate work done, it matters what was the initial position, what was the final position, what is the displacement. Because of the same reason, potential energy difference can be defined, not potential energy. Alright? It is always the difference which we can define. But good news is, we can assume potential energy to be zero at a point. Since it is a relative quantity, alright, I can say, alright, this point is zero potential and this point is that much potential. Understood? For example, if I take the same example, alright, please write it down, by the way. Suppose if I take mass of 2 kilogram to the height of 5 meters. Okay, suppose this is position A and this is position B. Alright, suppose if I take this mass to this, then what is the work done by external force? Work done by external force is mg is 20, this is 5, so 100 joules. So external force has done 100 joules of work. Alright. Now what is the meaning of this? It means potential energy at B minus potential energy at A is equals to 100. Alright. Now I can say that UA is equals to 0. This is what is important. Alright. After this, you are the king of your own will. You can say UA is equals to 0. In that case, UB is equals to 100 joules. Okay, you can take any point to be reference. You can say UB to be 0. In that case, UA will be minus 100 joules. You can take any point to be reference and the reference has zero potential energy. Alright. So I will write the next point. I hope this is clear to all of you. Is it clear to all of you, Shillong, Jia, that we can only define the potential energy difference and potential at a point can be taken as 0. That's it. And we call that point reference. Okay. In this case, A is reference. A is reference. In this case, B is reference. We measure potential energy for a point with respect to a reference. Is that clear to all of you? Okay. Understood? Is that clear? So the thing is, since we can only define difference in potential energy, we cannot exactly know potential energy at a point. Okay, but we can take a reference which has zero potential, all right, which has zero potential. But we can take a reference of zero potential and then find the potential energy at that point. Okay. So normally you cannot directly calculate potential energy of something, all right, of potential energy of at a point. However, you can calculate potential energy difference. So when I say I have done 100 joules of work, it means the potential energy difference between 2 points is 100. Now that does not mean that you can know potential energy of a certain point, all right? We cannot. But what we can do, we can assume, okay, I'll take this as reference, and reference is a point which has zero potential energy. Okay, and from that reference point we can say, all right, A is 100 joules, or 100 joules potential energy, or B is 100 joules. So I'll still take this example again, okay, like this one. Control C, Control V. Okay, this one. So if you take this example, work is done here, all right, work is done by force, how much? 100 joules, all right, work is 100 joules. That means the potential energy difference is 100 joules. So this is what we can calculate, all right. We cannot calculate UB or UA, but we can assume that A is reference, all right. If I say A is reference, if A is reference, in that case I'll take A's potential energy to be 0, and then potential energy of B will become 100 joules. Okay, understood? Is that clear? Sir, if 3 points are given, huh? Okay, now let's say if there was point B as, I mean C as well. Okay, if there is point C here, maybe I'll do it on next page. Okay, so let's remove all this crap, and let's say if we have 3 points, we have a point in between, this is C, and it is at a height of, let's say, 2 meters. Okay, now suppose we have 3 points. All right, if I want to calculate what is potential energy at B, what is potential energy at C, and what is potential energy at A, individually we cannot do, but what we can do, I'll say, let's say potential energy at A is 0. I'm taking this position to be my reference. Okay, I'll say potential energy at A is 0. Okay, I'm assuming this. If you can assume this now, then you can calculate potential energy at B and C. Very simple. See, work done by external force is equals to change in potential energy. Alright, so we will do it in 2 different ways. First, I'll take my body from A to C. Okay, first I'll take my body from A to C. If I take my body from A to C, then what will be the force? What will be the work done? Work done in that case will be equals to weight, which is 20, into displacement, which is 2. So 40 joules. Okay, and according to work energy theorem, this 40 joules is equals to UC minus UA, isn't it? Work done according to the statement, work done by external force equals to change in potential energy. Alright, so 40 joules of work is equals to UC minus UA, and we are assuming UA is 0. That would mean UC is equals to 40 joules. So we have calculated UC, and we had already calculated B was 100 joules in the previous example. If 3 points are given, then you can find out the potential of the other 2 points in the similar method. Is that clear, Jia? Understood? Now still, some of the students will not be satisfied, and in a similar way, some of the scientists were not satisfied by this. So what they did, they said, let's take a universal reference, alright, to remove this ambiguity. Let's say a universal reference, Alright, and that universal reference was decided to be infinity, because infinity is a point which is at, it is at such a vast distance that essentially there will be zero effect of anything there or at that point, because it is very, very far away. So generally, how we have defined zero potential energy at infinity. Okay, that is why if you want to calculate potential energy, let's say at point A, if you want to calculate potential energy at point A, okay, and nothing is given. So what I will do, I'll move a mass from infinity to this point. Okay, I'll move a mass from infinity distance, from a really far away distance to point A, and then I'll calculate what is the work done. So work done in moving a charge from a mass from infinity to A, this will be equals to potential energy at A minus potential energy at infinity. Is this clear? Alright, and this is zero because potential energy at infinity is zero. So potential energy at A is equals to work done in moving the mass from infinity to A. Okay, which is equals to F dot dr integral from infinity to Ra, where Ra is this position vector from certain point, okay, and R infinity is this. Is that clear? Understood? This is the formal or the general formula for potential energy, okay. So potential energy is equals to integral of F dot dr from infinity to that point Ra, and that will be the potential at A. Okay, please write down this formula. Even though we will not use this formula at each and every time, we will use the simpler ones, the derivation, we call it derivatives. Derivatives means the subparts of this. All right. Is that clear? I should not say subpart, I should say the results of this, the simpler results. So that is how we calculate potential energy at a point. Guys, remember, still we are defining this potential by the use of difference of two potential energies. Okay? Still we are using the difference, not the exact potential energy. Alright. Now suppose if the force field is given and if you want to calculate potential energy, alright. Suppose, see, this is what? You have calculated potential energy at a point from the force, alright, from the forces equation. But suppose if potential field is given, potential energy field is given, then how can we calculate the force, alright. So, the next topic is finding force from potential energy field. Okay, potential energy field. So imagine potential energy is given. Okay, potential energy is given as a function of x, y, z. All right. So for example, potential energy is 5xy minus 8z or y square z joules. So suppose potential energy is given like this. It means for different xy we have different potential energy at points, isn't it? Makes sense. Suppose you have potential energy in this form. Okay, if you have potential energies in this form, can we calculate force from this? All right, how can we derive what is the equation of force in this 3D space? Understood? That is the problem. So how to solve it? Potential energy, or you can say du, is equals to F dot dr. Okay. Now this F was what? This F was the external force. Okay, and please focus here. We defined difference in potential energy as the work done by the external force. Here also, it is the work done by external force. Don't go to your book and say, sir, you have given the wrong formula. Okay, this is external force. This is external force. Now, we can define all these things in terms of the conservative force as well. All right, how? Remember, our external force is enough just to balance the conservative force. Okay, but the direction is opposite, so I'll write negative sign. Your external force is the negative of conservative force. And because of that, I can write potential energy at A is equals to negative of integral from infinity to Ra F conservative dot dr. So when you define in terms of conservative force, you will attach a negative sign. Is that clear? Alright, when you define this thing in terms of conservative force, you will use a negative sign. Alright, so let's proceed. Yeah, here. So this was the external force. In terms of the conservative force, and this is what is used oftenly, alright? So I'll write minus F dot dr. Just remember this, where F is the conservative force, and mostly this is something you would deal with. Okay, it is the conservative force. So from this equation, because du is equals to minus F dot dr, and it is a 3D equation, then to define force, we have to use the partial differentiation. So it is equals to minus del u by del x I cap minus del u by del y j cap minus del u by del z k cap. Okay, and this del u, this is not d or something else, this is known as del. Alright, it is a partial differentiation. Is that clear? So from this equation I can say Fx is equals to minus del u by del x, Fy is minus del u by del y, and Fz is minus del u by del z. Okay? Understood? Now let's discuss what this weird kind of shape means. Alright? What does this del, or what is, see, this is differentiation, but a special kind of differentiation. It is known as partial differentiation. Okay? I don't know whether you have heard of it or not. It is known as partial differentiation. Okay? It is known as partial differentiation. Clear? Okay, now how do we calculate the partial differentiation? So first of all, we have to learn how to calculate partial differentiation. But before that, please copy these formulas. Okay, please copy these formulas, everyone. Whenever done, please let me know, then I'll explain. Okay, what about you, Shillong? What about you? And by the way, Shillong, do you also have protests? Are you seeing any protests in Meghalaya? If we talk about Assam, the condition is really, really scary there at Assam. And I guess up to a certain degree in Manipur also. But what about you, Shillong? Is everything okay? I hope it is okay in Shillong regarding those protests and burns and everything. Oh, today no. All right. By the way, I really hate these buns and everything. But see, as citizens of democracy, ultimately this is the only weapon people have, isn't it? Strikes and dharnas and all those things. But ultimately, there are two aspects of the strikes and buns. Like I said, it is the only weapon people have. Ultimately, they have to choose this. Second is sometimes people misuse it, and they just bother everyone, and they make life difficult for everyone without any apparent reason, for no good use. But sometimes this is good. All right, like something is going on. All right, I should not get politically here, but something is going on in Hong Kong, and those people are actually fighting for their life in Hong Kong. So that is how countries are made. That is how civilizations are made, through protests. Not a big fan, but yeah. Okay, let's do this question. The question is, suppose potential. I'll learn by what is partial differentiation. Okay, what is partial differentiation? So what is partial differentiation? Imagine we have z as a function of x and y. Okay, suppose this is a function. And I want to find out, see here, z, x, y, everything is variable, nothing is constant. If I want to find del z by del x, okay, we cannot find the net differentiation, but we can find the partial differentiation. So how do we calculate partial differentiation? So partial differentiation is calculated just like normal simple differentiation, but only difference is, when we are doing it with respect to x, treat y as constant. Okay? We have to differentiate z with respect to x, treating everything as constant. I should write everything. All right, let's write it in a better way. The meaning of this is differentiate z with respect to x, treating everything else as constants. Okay, treating everything else as constants. So I will do this question, and I hope by this you will understand. So del z by del x is equals to differentiation of this whole quantity with respect to x. Okay, y must be taken as constant. So what I will do, I'll just write y, differentiation of x is 1, minus y square constant, differentiation of x is 1, plus differentiation of x square is 2x. So it is equals to y minus y square plus 2x. This is the value of del z by del x. Okay, remember we are saying is del, not d. Okay, in the same way, del z by del y, what is the meaning of this? Differentiate. Okay, maybe I will copy it. Work smarter, not harder. Yeah, I'm not saying I'm smart. I'm saying I'm lazy. Control C, Control V. The only difference is, instead of x, we must have y. Okay, differentiate z with respect to y, treating everything else as constant. That would mean del z by del y is equals to, this will become x, this will become minus 2yx, and this will become 0. Is this question clear or not? Shillong and Jia. This was the function. This was the function. Clear or not? This is how we calculate the partial differentiation. Understood? Shillong, what about you? Pakka? Okay, let's do one question. Suppose z is given by y sin x plus xy cube minus y square. Alright? Find del z by del x and del z by del y. Tell me, what will be the answer? Sir, if y is constant, it's differential. See, where? If y is constant, its differentiation will be 0. Yes, but there is no simple y here. See, you differentiate this. Differentiate xy with respect to x, treating y as constant. So, imagine if it is 5x. What is the differentiation of 5x? It is 5, no? Alright, that's what I have done. Don't differentiate 5 itself. For example, when we are differentiating with respect to y, x is constant. Alright, see, the differentiation of x square will be 0 in that case. The differentiation of x square will be 0 in that case, no? Do this question. In fact, maybe you can write x as well. Okay, now do it. Y sin x plus xy cube minus y square plus x. What is del z by del x? Shillong, this is sin x. Differentiation of sin x is what? Cos x, yeah? See, you have to differentiate sin in the first. So this will become y because y is constant, so y cos x plus y cube is constant, differentiation of x is 1, differentiation of y square is 0, so minus 0 plus differentiation of x is 1. So it is equals to del z by del x is equals to y cos x plus y cube plus 1. Okay. Shillong Center, y square has to be constant, no? Alright. Now differentiate z with respect to y. In that case, sin x will be taken as constant, differentiation of y is 1. So sin x, differentiation of y is 1, plus, then x is constant, differentiation of y cube is 3y square, minus differentiation of y square is minus 2y, and differentiation of x, which is constant, is 0. So del z by del y is equals to sin x plus 3y square x minus 2y. Is that clear or not? Or not? Yes or no? Is this question clear to all of you or not? Pakka? Shillong Center? Is it clear? Alright. So, let's say the potential energy is given by 5xyz minus y square x plus zy square x minus x. Suppose this is, alright, I am just giving you random values. And we have to, from this, we have to find the equation of force. Okay? The first question will be done by me. So first of all, we have to find the components. Fx is defined as minus del u by del x. Fy is defined as minus del u by del y. And Fz is defined as minus del u by del z. Okay? Would you like to give it a try? Would you like to give it a try? See, Fx will be equals to minus, what is del u by del x? It will be 5yz minus y square plus zy square minus 0. This will be Fx. Fy will be minus del u by del y. So it will be 5xz minus 2yx plus zx 2y minus 0. Oh, this will be minus 1. I'm sorry. One mistake. This will be minus 1. Okay, and this will be 0. And finally, Fz is minus del u by del z, so it will be equals to minus 5xy minus 0 plus y square x 0 minus 0. Okay, we have Fx, we have Fy, we have Fz. Alright, and then all we need to do is write the force. So force is equals to Fx is how much? Minus 5yz minus y minus minus plus y square minus zy square plus 1. This much I cap, because it is Fx I cap. Because what is force? Force is Fx I cap plus Fy j cap plus Fz k cap. Alright, that is what I have done here. Okay, so this is Fx I cap plus Fy minus 5xz plus 2yx minus 2zxy j cap, and finally plus minus 5xy minus xy square k cap. Understood this question? We just have to do this. Okay, this is how we can calculate the force. This is the equation of the force. All right, it is in a slightly bigger question, but still the principle is same. So let me see a question. Okay, we don't have right now any question from the force field. Maybe I can give you a question. Okay, remember at the very beginning I wrote the formula. Yeah, this one. 5xy minus 8y square z. Okay, so find the force. Find the equation of the force. Find the equation of the force. This is the question. I want answers from all of you. Find the equation of the force. And don't forget the negative sign. Force is minus del u by del r. Anyone with the answer? Very good. Correct answer. Okay, Shillong, I'm waiting for your response as well. See, Gia has solved it correctly. Very good, Gia. That is the force. Very good. Okay. So, fx is equals to minus del u by del x. So, minus, this will be equals to 5y minus 0. Okay. So, it is equals to minus 5y. Correct. Fy is equals to minus del u by del z, or del x. It is equals to minus, this will be equals to 5x minus 16 yz. So it is equals to minus 5x plus 16 yz. Is that the same answer? Yes. And fz finally is how much? Minus del u by del z. It is minus, this will be 0, and minus 8y square. So it is equals to 8y square. So ultimately the answer will be fx I cap, so minus 5y I cap, then plus minus 5x plus 16yz j cap, and finally 8y square k cap. All right. Okay. Yeah, let's talk about, stable, unstable, and see, let's talk about stable, unstable, and neutral equilibrium. Okay. See, if you want to have a stable equilibrium, what do we mean by stable equilibrium? Stable equilibrium is it is a kind of equilibrium where the body is at rest, or it is at equilibrium, I should say. It is at equilibrium and it is stable. Means if you displace something very slightly, if you change a certain thing very slightly, then it will again return to its original place. For example, imagine this, all right, this kind of U-shaped road, and we have a ball here, all right. It is at equilibrium because normal is equals to mg, okay, normal is equals to mg. It is at equilibrium, okay, equilibrium means net force is 0. Now it is at stable equilibrium. Why? Because if you displace it slightly, it will go up, come down, go up, come down, and eventually it will come down to its original position. This is what we call stable equilibrium. All right. Now, what is the condition of stable equilibrium? Potential energy must be minimum. Potential energy is minimum for stable equilibrium. Okay, potential energy is minimum for stable equilibrium. Then we have neutral. Okay, what is neutral equilibrium? Neutral equilibrium is like a straight road. Okay, the body is at rest. Again, n is equals to mg. It is at equilibrium. But if you displace it slightly, then it will, it will move ahead. It will change its position. Potential energy here is 0. Okay, and finally we have unstable equilibrium. Now what is unstable equilibrium? Potential energy here is maximum. Okay, if you have maximum potential energy, then that will be unstable equilibrium. For example, this kind of thing. If you have a body here, it is at equilibrium at this point of time, but if you slightly change it, if you move it slightly, then the ball will roll down the inclined plane, it will not come back. So that is an example of unstable equilibrium. Okay, it is related to potential energy like this. Okay, now what is the condition? The potential energy, d square u by dx square must be positive. Okay, basically the rate of potential energy is the rate of, you can say, force is increasing. Here it is d square u by dx square is 0, and finally this one is d square u by dx square is negative. Alright, it is negative. That is how we can check whether something is at stable equilibrium or unstable equilibrium. Got it? So these are the conditions. Okay, remember this. So just to summarize, stable, neutral, and unstable equilibrium. I will write EQBM. EQBM. I hope you will understand. So du by dx is 0. Du by dx is 0. In three different, in all the cases. But d square u by dx square must be positive for stable. D square u by dx square must be 0 for this, and d square u by dx square must be negative for this. Potential energy here is minimum. Potential energy here is, we can say 0, and potential energy is maximum at unstable equilibrium. All right, and finally, let's try to understand it. We have this, and we have this. So what is going on? If you, if you just take it forward, if your dx is positive, all right, and your potential energy increases, all right, your potential energy increases, your force must be negative. All right, your force must be negative. So basically, if your potential energy is increasing, guys, what is F? F is minus du by dx. Okay, so if this is positive, if this is increasing, then your force is negative. Your force is negative means it is pointing towards the other direction. That is the condition for, stable equilibrium. On the other hand, if you take this position here, if you take this body here, all right, okay, if dx is positive, then what will happen? The force will be in this direction, all right, because du by dx is negative, potential energy is decreasing. If du by dx is negative, then force will be positive. If du by dx is negative, then force will become positive. It means it will be in the same direction. Hence, the body will have, a runaway effect. So, this is an unstable equilibrium, this is stable, and this is neutral. Here, du by dx itself is 0. So, guys, that's it. That's it for today's class. Today, we have discussed potential energy. In the next class, we'll continue work energy theorem. We will include potential energy in this, and we'll do lots of questions. Okay? So, thank you. Bye-bye. Good night. See you.